What a talk to follow up on. Well, here's how not to be charismatic. But what I can bring to you today is a lot of enthusiasm for this particular topic. I've been really interested in authorization and authentication topics for many years now, and I've been digging quite deep into how OpenID Connect and OAuth 2 works, and learned a hell of a lot of things. Previously did a little bit of a talk on how it all works, but today I'm going to teach you how to hack it. It's a bit of a smorgasbord of just various things I've used as a pen tester at ZX Security. I've brought to the table whenever I've encountered OpenID Connect, and I'm hoping I might be able to share a few of those experiences with you, and maybe it might give you some ideas as pen testers. Also as defenders as well, because I imagine not everybody here is a pen tester, and you're probably wanting to stop people like me. So, yes, as I said before, I'm Matt. I'm from ZX Security. I'm a security consultant. I do a lot of pen testing things, but I've come from the blue team back in the day. I was embedded into the security team for a few different companies. And as you might also be able to see here, I have an absolute love of cheesy hacker stock photos. So trust me, the slide's going to be full of them. So hopefully they're going to be enjoyable for you as well. And if not, I apologize. So to keep this talk nice and short, rather than taking up the rest of your day, because trust me, this is a huge topic, getting it into half an hour is quite a lot of fun. We're going to look into just 4 different sort of scenarios that pen testers might find themselves in when they're encountering OpenID Connect and OAuth 2. So we'll be looking at things when we're exploiting, say, a website without any prior credentials. Looking at exploitation using an attacker's own account. So if you are able to register your own account, but maybe not attack somebody else's. We'll look into scenarios where we manage to steal somebody else's account and what we can do with OpenID Connect in those circumstances. And then lastly, what we can do if we manage to steal some service credentials, such as a client ID and secret, what we might be able to do to go and further attack or pivot into other systems by exploiting OpenID Connect implementation flaws. So, quick background on OpenID Connect and OAuth 2, because it is a huge sort of thing, but you've probably encountered it in the past. OAuth 2 sort of came about as a modern authorization framework. It was largely there just to go sort of standardize third-party access to APIs, really. It wasn't really supposed to be used as a login system, but people kind of butchered it in order to go and do that, and it wasn't really what the protocol was designed for. So what happened was OpenID Connect came about and basically became a superset of OAuth 2. So it's OAuth 2 plus some extra stuff, and that brings to the table the authentication aspect of it. So who you are, what sort of attributes you have as a member of this particular identity provider. There's also a bunch of concepts here we'll quickly go through. If you think of it as, we've got here a resource owner or a user. What they typically will want to interact with is confusingly called a client. Think of it actually as the server. This is the thing that we're trying to actually log in as, such as this fictitious photoviewerplus.co.nz, which brings Google Photos into it and helps display them to you, and you can manipulate them or something along those lines. So the resources that they're bringing across here as these photos. So the resource owner owns resources. And these are usually stored on the resource server. So with me here so far, it's sort of all making sense. And this is typically some sort of like API. So we can imagine api.google.com is where you go and get your photos from, something along those lines. And to tie it all up, we've now got our identity server as well, which is, say, Google logins. So instead of it being that sort of browser server sort of aspect here, we've now got 3 different servers, and there's quite a bit of complex dance in order to go and do a thing where we can log into the client without giving the client our Google password and also giving it access to our photos. Just going to move that a little out of the side there. So how does this sort of untrusted third party get access to this in the first place? Well, first the client will go to, the resource owner will go to the client. They will see a page like this, which has a sign in with Google button. They click the button, and what happens is it actually ends up going off to account.google.com or something along those lines. Google, in this case, will show a login page. They log in with their password, and what we get back, the the, 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 This authorization code token is a one-time use token that the resource owner can't use, but the client can. What happens is they get redirected back to the client. The client then, with its client ID and secret through a back channel, will then exchange that with the identity server to get an access token. And this access token is what we can use to say who this particular person is. We trust this because it came from Google servers. So the user now sees a page that says, hey, cool, please wait, we're just retrieving your photos from Google. What will happen from there is that token can also be used to go and access the resource server using specific permissions that the user consented to while logging in, and the photos are then transferred over to the client so that they can be displayed. I'm cutting through a few details here, but this is just to get you all up to speed. There's actually a couple of other flows as well. The one that I just demonstrated here is called the authorization code flow, named after that particular token. There's a couple of others as well. We've got device code flow, which is what you use when you're logging into things like your TVs or your photo frames or whatever. It's where you don't necessarily have a browser that you can actually use to do the login. You have to use some other device. And then the last one, as well is the client credentials flow. This is when you don't have any resource owner whatsoever. It's usually just server-to-server stuff, like the photoviewerplus.co.nz wanting to get its billing information from Google. It's just when it's logging in as photoviewerplus. Cool. All up to speed, hopefully. That's the whole protocol in 5 minutes, which definitely has glossed over a lot of details. We'll go into that a little bit more as we get through this. But our first particular scenario we're going through here is the exploitation without credentials. So imagine you've got a website here and you have no way of logging into it. You can see the front page, you can see a login screen, and you know it's OpenID Connect, but you don't actually know how to get anywhere further. What we can do as an attacker or as a pen tester is we start with a little bit of reconnaissance. There's some really handy little features of OpenID Connect and OAuth 2, such as the OpenID Connect metadata URL. This is usually found at this particular location here. There'll be a URL which ends with this. Usually it's just at the root of your identity server. And if you go to it, you'll get a bunch of JSON. It's just a whole bunch of information about how this whole thing's set up. But there's usually some really interesting information you can get out of this, such as the keys, the public keys that are used to go and sign things, what kinds of keys are being used, so that HS256 there. There's an admin claim here. I wonder what that does. That sounds powerful. And then you've got this refresh token thing down the corner here as well, which we can potentially use to gain persistence. We'll go into that a little bit later, but it's a really good place to start. Just gets you a good feel for how it's all working. I mentioned that web keys place before. It's a really awesome one to look into as well. Usually that's a follow-up URL that has a list in a very specific format of what the public keys look like. I've found in the past that sometimes people are using 512-bit RSA keys to go and sign access tokens and all sorts of things. For some of the folks here, probably know that's a wee bit too weak. These days it's probably quite crackable. So yeah, make sure that those keys are nice, good length, and they're generated properly. Or as an attacker, hopefully they're not. Second thing is have a look at the login page URL parameters. We can click on the sign in with Google or whatever button. We can't log in, but we might be able to have a look at see what the parameters on that it looks like. So when you click on it, you go directly to a page that looks like this. And this looks like basically a bunch of gibberish right off the bat, but if we have a look a little bit closer, we can see some interesting stuff like this client ID. It looks like it's an incrementing number. I wonder what happens if we start incrementing that further. Can we iterate through all of the current the clients that are supported by this identity provider? These scopes, again, there's that admin one. What does that do? That sounds kind of powerful. If we request it, does something happen? There's the redirect URI here. Usually this is an allow list of specific URLs that you're allowed to redirect the user back to. What happens if we change this? Does it suddenly error out? Does it appear that there is a safe list, or are they just allowing anything? And then lastly, we've got the state parameter. We're going to go through this a few times, but essentially, when the client sends somebody off to the identity provider, that needs to come back with the exact same value. Now, the client can set whatever the heck they want with that, and they need to match it with the user that they were specifically sent away with. But sometimes the clients stick all sorts of weird and interesting information in there, such as the origin server here. Well, why is that there? But maybe we can use it to get past a WAF. Or this auto-promoted staff equals false. Turn that on to true, see what happens there. And then lastly, just Do your usual basic pen testing fluff. You know, like, can we just use basic auth? Can we skip all of this OAuth crap? Are there any leaked credentials in the source code, et cetera, et cetera, et cetera? So, as somebody who isn't a pen tester, you're probably quite interested in going, okay, right, there's a few things here I need to worry about. What do I do to go and defend against this sort of stuff? So, for these ones here, really good idea is just to go and disable any unnecessary features. If you've got any sort of sensitive or dangerous scopes that generally aren't going to be accessible to the public and maybe they're only used internally, just hide them. You don't need to advertise them in that metadata URI if it's not necessary. Try and do it anyway. See, hopefully it shouldn't break anything. Disable any unneeded keys. You notice there we had two, like there was HS256 and RS256 in that big as JSON thing. Those are two quite different ways of doing encryption. One's symmetric, one's asymmetric. Do you need them both? Can you just disable one of them? That'll reduce your attack surface. Check your defaults as well. Like I mentioned before, there was an identity provider I saw that was using 512-bit RSA keys by default. Check those defaults, make sure they're set to strong, proper values. And again, look at those leaky parameters as well. Sometimes that state header can leak some really weird and interesting stuff. Lastly as well, review your trust boundaries. So that's where your which data has been sent and received by specific components. Throw it into something like Burp. Just have a look at the data that's actually whizzing around when you're doing a login process at the HTTP layer. You might find that there's some stuff here that you didn't particularly want revealed. Can some of those parameters be encrypted and signed? You can usually do that with the state parameter. Lastly, apply your Stride threat modeling as well. Map out your solution. Draw up your trust trust boundaries and see when data crosses over those. When you do that, apply Stride and see whether you can see if there's anything you can do to help protect that a little bit further. Cool. So for our second scenario, we've got exploitation with our attacker's account. Now, of course, this is not somebody else. We've just signed up an account. Now, as a result, we can get a little bit further into things. Maybe we don't have privileged access, but we still we'll still be able to access most of the site, and we can see how some of that bit more of that login interaction working. So, as an attacker, like I mentioned before, there's that state parameter. It's a really important thing when you're doing, especially with that that authorization code flow, that you get that particular one right. Or, as a pen tester, it's really great if we're not getting it right. So again, it's usually sent when it goes off from the client off to the IDP, and then it should come back exactly the same state. But if they're not doing that properly, and it's not being matched to a specific user, we end up with things like session fixation attacks. How that ends up looking is, if you remember this particular slide where we sent off our Google password and it came back with an authorization code for us to use, if we weren't doing the state parameter thing properly, what we could do is we could just make our own account as an attacker and make it look exactly like the victim's account. We send our password off, we get that authorization code back, but we don't send it to the client. Instead, what we do is we craft ourselves up a really awesome, like an instant messenger or an email or something, and say, hey, bro, check out this cool-ass link. It's that photoviewerplus.co.nz that you love. And, you know, they've done their cybersecurity training. They know that not to go and click on random links that they receive in emails. But this is a friend, right? They look at the link and it's like, oh, yeah, definitely photoviewerplus.co.nz. There's that HTTPS thing in the background there. Yeah, I mean, there's all that other shit there, but it's just computer stuff, right? I'll just click on the link, should be right. And what happens is instead they end up getting logged in. They finish the login for us, and now they're logged in as our attacker account, which looks like their account, but it was crafted so it's actually our one. As you can see, logged in as hackedyou at pwned.lol. They might not know that they're actually sitting on our account, and then they start uploading sensitive photos or doing things in a way that, you know, now we've got access to their account, we now have access to that particular data. This is just one example. There's a whole bunch of different ways that you can abuse session fixation, but this is the sort of thing that is designed to prevent. Another area to investigate is what we call, what we're referring to as open client registration. So sometimes you've got big login servers like Google's one where they want third parties to go and use their awesome login button and do a little bit of advertising on every single site by having that button there. So what we could do is we could make our own client that kind of looks like a legit thing of something else, and then we can go phishing. So if you've ever logged in with, say, Azure AD, you might be kind of familiar with a screen like this. I've cut out some information so it's a bit easier to see. But long story short, there's a really cool app that Microsoft has made called Graph Explorer. It's really good as a developer for testing out various APIs and things. And so that Microsoft really know that, so you're absolutely sure that you're dealing with a Microsoft thing, because you're granting it read-write directory data permissions here. It's kind of scary. They've put a big plus thing on the side of it there, so you definitely know you're talking with Microsoft. So they've done it well. But if you can imagine somebody who doesn't have that particular feature, we create ourselves an organization called Microsoft with ones and zeros, and then we just make a client that looks exactly the same icon, same sort of thing, and request the same sort of permissions. If you give somebody that link and say, hey, can you log into this cool tool? They might redirect off to you with a valid credential that has read-write access data, and they don't realize that they're not actually interacting with real Microsoft, they're interacting with something that's fake. And again, they're just going to click on that link. They've done their cyber training, right? They see the HTTPS, and they see that it's login.microsoft.com. They know that they can trust that link. And lastly, we've got JOT attacks as well. Now, JOTs aren't exclusive to OpenID Connect, but they're used quite heavily in it, and you'll see it quite commonly through there. And JOTs, there's a lot of implementation issues that you get with a lot of those things. I'm not going to go into too much detail about these ones, because a lot of these discussions have been done to death. But really, really quickly, alg-none is one particular attack you can do with JOTs. This is what a access token might look like, where you have a thing which is signed by a HMAC key, totally legitimate looking thing. What we can do is we can just go into the header and just say, oh yeah, this JOT isn't signed at all. There's no signature here. You just anything's in there, whatever you want. And just because we've just put none there, and the spec allows this, it goes, oh yeah, this is a valid JOT, because the spec says you can just put none there and then don't sign it, and that's a valid JOT, which is really stupid. Most people ignore that particular part of the spec and say, yeah, okay, no, it has to be signed, but some people don't, and this has definitely caught some folks out. The other popular attack you will see is key confusion attacks. Now, there's quite a few different varieties of this as well, but one particular way you do this is, say you've got this particular JOT here, it's signed using an RSA key, and this is this specific kind of key here, which you'll be able to look up using that OpenID Connect metadata thing, signed using that key. What would happen if we were to say, actually, this is an HMAC key, but use that RSA key that you can look up on the thing. So what it does is it goes over and looks up the RSA key, but it goes and grabs the public key, of course, and since it's a symmetric cipher, it uses the public key that we have access to sign the JOT, which of course, the public key is then also used to verify the JOT. Now we can just go and make our own keys. There's loads of information about how to go and do this particular attack. I'm not going to go too much into detail about that one, but definitely look it up. It's really interesting. So many clients were out there were vulnerable to that particular problem. But there's a third kind of attack I do want to actually go into a little bit, which is what I call a forged issuer attack. And this is something I've nearly encountered, let's just say, in the past, where I saw a particular app which used the issuer claim here to say where the JOT token was coming from. And it used that particular thing. It looked that up first to say, okay, cool, I'll go and grab the public keys, and so I can make sure that I can verify this thing. You might be able to see the problem here is I could just then change this to point to where my key is and then sign a JOT that the server now trusts, because it's like, oh yeah, we'll go over this place and we'll grab the public key from there. The JOT's now signed using the attacker's key, and then we can log into things. And this is because they're not limiting what issuers are trusted. They just kind of allow it to just be anything, really. And it's also a bit of a problem because what you're supposed to really be doing is checking the signature first before you read anything else. Well, you check the body, then the signature here. It gets complicated. So, as a defender, validate those state parameters. Check when the user comes back with that authorization code, make sure it is a known, legit value. It isn't something that isn't expected. It's not something that has been tampered with or manipulated. Also, make sure that the state parameter matches the local browsing session. You shouldn't have sent somebody off and then a different person came back with the authorization code which matches that particular state as well. You want to make sure it's the same person, so match it with a cookie or match it with an IP address. Match it with a cookie, it's probably the best way to go and do that. And then when you do that as well, If you get an authorization code but somebody's already logged in, just prompt the user and say, hey, you're currently logged in as this, but did you actually want to log in as this person? Because it's a different one to that authorization code we got. And in that way, you might be able to help stop some of those session fixation attacks. Open client registration. If you're allowing third parties to go and register with your identity provider, consider disabling that client registration to the public if you don't need it. Seriously, it shouldn't be on. It's kind of got a little bit of, it shouldn't be on if you aren't explicitly needing it. It's kind of got a lot of attack surface, and I'm only just barely skimming the surface of that one. But if you do need to do that, manually vet clients before they can ask for dangerous scopes. We saw that read-write directory permissions scope that was being done there, and we saw that consent screen for it. Make sure that only clients that you have manually vetted are able to even request scopes like that. Mark some scopes as well as requiring an organization admin to approve. There shouldn't be really any reason that most people in an organization should request that scope. They're probably not going to need read-write access to the entire like Active Directory thing. But maybe some more organization admins can. So see if you can get them, like somebody who is more knowledgeable with it, to approve those notifications, those scopes before they get asked for. And then of course your JOT attacks. Make sure you just keep your libraries up to date. Trying to defend against these sorts of things, it's cryptography, it's really hard, it's crazy maths, I have no idea how to understand it. So keep your libraries up to date. They may, very official looking libraries fell victim to some of these things, but once you updated, it was resolved. Secondly, and I'm going to say this secondly, thirdly, and fourthly, don't write your own JOT parser. Please don't write your own JOT parser. Please don't write your own JOT parser. The thing with JOTs is they are deceptively simple looking, and anybody looks like they can go in and they can go and write these things, but they have many sharp edges that are really quite invisible, and it's really hard to go and know that you're doing this wrong, so don't do it yourself. Okay, third scenario we've got here is exploitation with a stolen user account. So let's just say we've managed to break into somebody's account. Maybe they have more privileged access to things than others normally would. And you know, we got through this through, hey, they've got a weak password, they don't use MFA, you know, all the usual sort of fluff with that as well. Maybe it was a little bit noisy though, and we don't really want them to kick us back out again. Maybe they got a notification with their MFA login, but we're using our awesome O-Day, like iCloud, iMessage O-Day to go and, like, you know, win against a pen test. We want to persist within this particular login, even if the attacker is kind of aware that something's not quite right. There's a few things we can do here to go and establish persistence with this. One of them is to use refresh tokens. Again, we can go and if we create if we've got our particular login here, you remember the slide where the client claimed their authorization code and they used it to go and get a JOT. What they can do at the same time is assuming the user allows this, they can also request a refresh token at the same time. Now this one is not usually a JOT, it's usually some sort of like just a random value that's just looked up in a database, so that way it can be a lot more easily revoked. But what we can do with this refresh token is whenever the JOT token expires, should only last about an hour or so, the client offline on a back channel can just use that refresh token to get a fresh new JOT. And what that ends up looking like is kind of, to the user is something like this. A lot of applications will have this sort of like connected to apps kind of thing. This usually maps quite well to what sort of refresh tokens have actually been issued. And it provides an area where you can go and revoke those those refresh tokens, so that when the JOT expires, obviously there's no more JOTs now because the refresh token doesn't work. So as an attacker, you can hide out in that sort of place by issuing a refresh token under a client that maybe looks legitimate. When the user resets their password, they might not know, or may not even know what the heck the whole connected apps thing's about. And even though they've refreshed they've changed their password, now you're still persisting within a refresh token that just sits in those connected apps lists. The second one, of course, is just excessive token lifetime. Like I mentioned before, JOTs should only last for up to an hour at most. But sometimes you'll see, sometimes we've seen engagements where people have issued a JOT and they've lasted way more than an hour. They've lasted like 30 days, or in this case, basically till the end of epoch time. And we can just persist with this. It's really hard to revoke a JOT just due to the way that it works. The whole idea of a JOT is that you can just look at it as its own thing, and then without your, you can look at it as its own thing. You don't have to go into a database and say, is this legitimate? You just go, oh, I've got this public key. Does the JOT validate? Cool, I trust the JOT. I'm just going to act on that. That makes it really hard to revoke. If you suddenly issue it and go, oh, actually, maybe I shouldn't have, it's kind of hard to do that without just entirely rolling your keys. The second thing I'll talk about here is dangerous scopes. So a lot of the time, if you break into those attackers' accounts, you might actually start seeing some interesting different scopes that are being requested as a part of their normal sort of login cycle, or as a part of functionality that's hidden away in admin panels. And we can start looking into those dangerous scopes and seeing if we can go and get ourselves further, or even get that access to that using just a regular account. So scopes are a feature of OAuth 2, but they are commonly abused to grant permissions to things. They shouldn't be the case. When you see that consent screen after you log in that says, hey, do you want to actually give this thing access to your email address and maybe read your emails as well? This isn't a permissions granting thing, it's a permissions boundary. What I mean by that is, if you have a think about a fictitious photo website where we've got a regular user, just a normal user who hasn't got a premium account or anything like that, and they have photo write and photo read permissions, right? But they modify the login session so that they also request the premium promote photo scope. So the access token that gets issued to something says, this access token is allowed to read photos and also promote photos as part of a premium feature. But the user that asked for it doesn't actually have the premium feature enabled. What this access token should be able to do in this case is the intersection here, not the whole access token part. And what we'll see quite a lot of the time is sometimes these scopes, if you request it, the identity server doesn't really know the subtle interactions of how permissions and access control works on random resource servers. So it just says, okay, this client's allowed to request this, therefore here you go, and now you've got access to premium features. It should be a boundary, not granting. Right, so as a defender, going back to that initial part about the persistence thing, inform the user about various connected apps. If the user resets their password because they're like, oh shoot, there's a hacker rumbling around there, I've got weird tweets promoting, I don't know, random scam stuff, maybe I'll go and change my password. After they change their password, tell them to review the connected apps. That way they might go, oh, hang on, I didn't really remember granting access to hacker scammer. I'll just revoke that token. Also vet which clients can actually ask for offline access. Depending on your your application logic, it might not be a thing that everybody requires. Maybe you might be able to limit that down to something where people have to be manually vetted. Limit the JOT lifetime as well. Like I said, shouldn't last for any more than an hour. If you need more access, either refresh the token using a legitimately issued refresh token, get a fresh new JOT, or you can transparently send the user back to the IDP and come back again with a JOT using the cookie that's stored with the identity provider. Use refresh tokens of offline access. I have got those around the wrong order. Ensure scopes limit access and not grant it. Like I said before, it should be that intersection, not the entire list. A JOT with an admin scope doesn't just make them an admin. They've actually got to be an admin user as well. So check that the user's ID against the app's own access control, or check their roles to make sure that they are actually an admin, so that they can use that JOT with it. And our last one here, we've got exploitation with a stolen service account. So this is usually where you can jump into usually a lot of IoT devices will have the client ID and secret embedded in it. Mobile apps often do this as well, just due to the way that some of their authentication dances work. Sometimes you'll even find it just embedded into the source code in some web applications, like SPAs and all that sort of jazz as well. But usually the really interesting ones are where you steal it from a web server as well. But as an attacker, you can actually use some of these things to do more phishing kinds of stuff. One of my favorite ones that I've been really interested in digging into a little bit is device code phishing. So I mentioned that device code flow earlier. very close to finishing, don't worry. Device code flow is what you'll normally see if you're, like, say, logging into YouTube with your like a YouTube app on your TV. You'll see like a QR code, please scan this, or go to this URL and type in this code. And what ends up happening here is we can, we can abuse this for phishing. What we could do in this case is abuse this particular login to steal it out of, say, an email client. So we've got a desktop email client, it's got a client ID and secret into it, we can decompile it. Maybe we can use it to impersonate that particular client. So we can use that client ID and secret, and using the device code flow, we say, hey, can you get me a link so I can log this person in using their phone, not their desktop? And it goes, yeah, sure, no worries, here's a link. We then go and bundle that up into an email. We say, hey, here's this important email, the URL's safe, see? They've done their cyber training, they know that the login.microsoft.com URL is safe, they can click it. And what happens is they will see a screen that looks like this. Hey, email client for Windows from legitimate software company would like to read your email. They got it in an email, so well, of course my email client wants to read my email, I'm looking at email. So you hit the accept button. But what happened, they've done their cyber training, they can see the login phone, all that sort of jazz, and it's from a legitimate software company, a company that they trust. Now, what happens in the background, the way that the client, the device code flow stuff works is it'll just constantly poll in the background saying, hey, is that link done yet? Is it done yet? Is it done yet? As soon as they've logged in, their phone just goes, yep, cool, just turn off, close the tab, and we get a refresh token that we can now use to go and read their emails. Last things, I'll very quickly go through this. Predictable client IDs and secrets. Have a look at those client IDs and secrets that you've stolen. Maybe they're incrementable because they're not some sort of like randomly generated thing. You might be able to just iterate through them all. And also, does the client secret look kind of human-made? The idea is that developers shouldn't be able to choose their own client ID and secret values because they're just things that computers are using to talk to each other. But if they're allowed to choose a password, maybe we can use our usual pen testing fluff to go and like see if they're reusing the passwords or they've chosen weak values. And lastly, we've got lateral movement as well. I will skip very briefly over this because I'm running a little bit over time, but long story short, if we manage to get access to a resource server, but multiple resource servers are trusted with a specific JOT, we can, say, hack this particular server, watch different JOTs whizzing around, but they're the same value. The JOT's accepted in all of these various different servers. What we could do is we could steal one of those JOTs and then we can get access to a different server by just replaying it to a different server. The idea is that you should be limiting the number of URLs inside that audience client, the audience claim there. It also can leak some of those internal ones too. As a defender, again, phishing, disable one of those unnecessary code flows, highlight dangerous scopes on the screen. This thing's trying to read all of your email. Do you really want to be allowing that? Predictable client IDs and secrets. Force a non-predictable client ID when developers sign up for a new client, third-party client registration, such as a GUID. And also force a long, randomly generated client secret. There shouldn't be something that's like a password. Don't let developers choose the values. Lateral movement as well. Limit the audience of each JOT, especially powerful ones. Don't let them exceed a specific, don't list them all in there all at once if they've got powerful permissions. Have one JOT per server. Cool, okay, we ran through it a little bit over time, I apologize. I usually do this, I get way too excited about things and go on little tangents. But if anybody's got any questions at all, please do let me know. I'm quite happy to sit on the Discord and run through anything. And lastly as well, if doing this kind of work sounds like your jam, ZX Security is hiring at the moment. We're on the lookout for junior consultants across pen testing, cloud, and cyber security and risk as well. Reach out to anybody in the ZX team and we can have a chat. Cheers.